The date today is the 6th. The topic for your notes today is solutions in colligative properties. And so guys, in about 2 minutes, we're all going to be at the same point where you've got your conclusion question answered. And again, guys, don't go back and change your answer when you actually know the answer at the end of the day today. I want it to be your best guess, even if it's now incorrect. Again, I won't mark it wrong. And then guys, this is the topic for your notes, and we'll get started in just a minute. So guys, let's go for about another minute. If at the end of that minute you're not done answering the question, at least you've thought about the answer, and that'll provide your framework for what we're going to talk about today when we actually figure out why salt water's boiling point goes up. You good? Minute? Done? That was a minute. Do you need another second? Or are you okay? Okay. So guys, you know I love to do this because it's good teaching. So let me do this for you as we do every day. Let's help you understand how we're going to answer this question. So guys, literally, the last thing that's going to show up on this board is the answer to the conclusion question. By the end of the day, you are going to understand why salt water boils at a higher temperature. Here's the thing. To get you there, this is going to be our journey. You ready? Here's how today is going to come together. The first thing we're going to do is we're going to talk about what has to happen for water to boil in the first place. And if you don't know that part of the answer to that question is the intermolecular forces have got to break, you better not come take the test on Friday, guys, because you're going to die. Guys, you already understand some things about boiling. In order for water to boil, the intermolecular forces have got to break. You're going to find out in a minute that's not the complete picture. So guys, the first thing we're going to talk about is what has to happen in order for water to boil. Then the next conversation we're going to have is what has to happen in order for salt to dissolve in water. See where this is headed? So once you understand what boiling is all about, and once you understand what dissolving is all about, then you stick those two things together and you find out why salt water boils at a higher temperature. See the method to the madness? You get the idea? Okay, so guys, this is how we're going to start. Grab something you can take notes on, and I don't think you need to write down this question, but certainly you need to think about the answer. And guys, the question is this: why does water in Orem not boil at 100? And some of you are going, wait, why 100? But guys, you understand that, right? The definition of 100 Celsius is the boiling point of water. But your water didn't get to 100 degrees Celsius. So guys, why does water boil at 96 or thereabouts? Why does it boil at 96 instead of 100? What's the deal? It's an elevation issue, right? But guys, here's the deal. Water has absolutely no idea where it is. It doesn't know if it's at 4,500 feet. It doesn't know if it's just under 10,000 feet at the top of Temp. It doesn't know if it's at sea level in San Diego. It doesn't know where it's at. So it's really not an elevation issue. Why does elevation then change boiling point? What is it actually a matter of? Do you know? Yeah. Air pressure. Guys, that's the idea. This is a question of air pressure, and you've got to understand this. So this is what we're going to talk about now. What are the factors, and you probably want to write this down, what are the factors that influence the boiling point of water or any other liquid? And as Matt pointed out, guys, part of the answer is atmospheric pressure. So you all understand that when you're walking around doing your living thing, you are moving through our atmosphere. And our atmosphere is at about 70% nitrogen, about 18% oxygen, and then all the other little things thrown in for fun. But guys, you are moving through our atmosphere. You're all aware of that, right? So guys, why does the atmosphere have an influence on boiling point? You ready? Don't try to draw the picture, but let me explain this to you. This is why our atmosphere influences boiling point. Guys, it goes like this. If you were to go outside and if you were to go like this, you are now looking into outer space. But between your nose and outer space is 20 miles of air. Did you guys know that? That our atmosphere is about 20 miles thick. So when you look up, there is a column of air 20 miles tall sitting on your face. And guys, it's very, very heavy. So why are you not being crushed under all of this air that's pushing down? And the answer is because it also pushes up. It goes in your ears, up your nose, around your back, and it pushes up as well as down, and it smushes you from all sides and from the inside out. Thank goodness your body leaks. So you really don't experience this smush because it's everywhere around you. But guys, the question is this: how heavy is that column of air? Well, guys, the answer is on the board, but this doesn't make any sense to me. You ready? Here's the answer. This column of air for a cubit or for a square meter. So the idea is this: my desk is about a meter wide, and that's a meter. So guys, if we could weigh all of the air that is sitting on this much of my table, it would weigh 10,000 kilograms. What does that mean? Well, guys, during faculty meeting this morning, I got so bored that I actually started playing around on my phone and I did some math because I knew we were going to talk about this and I knew that that wasn't going to make any sense. So I did things that were maybe a little more reasonable. So what about this? An 8.511 piece of paper. What is the weight of the air that's sitting on that area? How much air is sitting on here? Want to take a guess? It blew my mind when I figured it out. Should I just show you the number? Guys, the answer is this. On that area, the air that's sitting on there weighs 1,350 pounds. That's crazy. That's almost, well, it's the better part of a ton. So now you're going, okay, so that's kind of crazy, but what does this have to do with the boiling of water? So then I did some more math. And guys, I figured out the area of a 250 milliliter beaker of water. So check this out. How much air is pushing down on the surface of this water? Are you ready for the answer? The answer is actually 88 pounds. There's 88 pounds of air sitting on top of this water. So in order for the water to boil, it not only has to break the intermolecular forces, but what else does it have to do? Push up against the 88 pounds of air that's pushing down. Do you get it? So here's then the question. Why does water boil at a lower temperature up here in Orem? Can you make the connection? Why does water boil at a lower temperature? Come on, you guys are smarter than this. Go ahead. Exactly, and why would there be less weight if we're higher up? There's not as much air. So guys, this is the deal. This weight, 88 pounds, this is the weight of the air at sea level. But if we move up here to 4,500 feet, that means that there's less column of air sitting on top of the water. And if there's a shorter column of air, because some of it's underneath us now, if there's a shorter column of air sitting upon the water, there's less push down, so it's easier for the water to get out, so it boils at a lower temperature. Do you get the idea? Questions on that, because guys, it's important that you understand that. So the big idea is this: in order for water to boil, it's got to be able to push back against the atmosphere pushing down. At sea level, that's 88 pounds of air pushing down on this much water. When we come up here to Orem, there's less air on top, there's less push down, it boils at a lower temperature, in this case 96 degrees. You get the idea? Okay, so guys, let's include that in our notes then, and it goes like this. So what factor determines the temperature at which liquids boil? Atmospheric pressure. But there's another factor, and you already know the other factor. What is the other factor that influences the temperature at which something boils? Intermolecular forces, right? You guys already knew that. So now we have the complete picture. We now understand the two factors that determine the temperature at which water boils. One of them is the pressure of the air pushing down, and the other one is the strength of the intermolecular forces holding it together. You guys good to there? Because I'm going to ask you a question that follows up on this, and if you understand this, you'll be able to answer the question. You sure you're okay? Okay, let's find out. So guys, the question then is this: what if we want to make water boil at a higher temperature? What can we do to water to make it boil at a higher temperature? And let's do atmospheric pressure first. Guys, what could we do to make water boil at a higher temperature if we wanted to mess with atmospheric pressure? What do? Go down, right? Go to a lower altitude. So guys, if water boils at 96 in Orem, if we go to sea level, it'll now boil at 100. What if we want it to boil higher than 100? What do? Go to Death Valley. Guys, you guys know about Death Valley, right? It's actually, have you ever seen those pictures of the F-16 pilots that actually zero their altimeters in Death Valley? You ever seen this? It's okay, this has nothing to do with it, but I saw a picture and it was really cool. Apparently in Death Valley, you know, it's below sea level, right? It's like 200 or 300 feet below sea level, and there's a line on a rock that says 0. That is sea level, and then the bottom of the canyon is down here. And so these F-16 pilots will take their jets into that canyon and fly them right at that 0 mark and make sure their altimeters say 0. Isn't that cool? I don't know why I thought that was cool. But what happens if you go down to the bottom of the canyon? You're deeper in the atmosphere, the pressure's higher. What happens to the boiling point of the water? Goes up. The boiling point at the bottom of Death Valley is almost 101 degrees Celsius. Again, because you're at an even lower altitude, higher atmospheric pressure. So guys, let's make sure we got that. So one of the things we can do is increase atmospheric pressure by decreasing elevation. You get the idea? Now guys, I promise myself every year that I'm not going to do what I'm about to do, and darn it, first period I said, all right, I'm going to do it again, and I wish I hadn't, but now that I've done it, I got to do it for you. Here we go. You guys all okay with the idea that if we go down in elevation, the boiling point goes up? You get it? So guys, what happens if we go the other direction? What happens if we continue to go up in our atmosphere? What happens to the boiling point? It goes down, right? And it goes down and it goes down and it goes down and it goes down until we get into outer space. And when we get into outer space, what is the air pressure? 0. There is no air. So guys, if there's no air pressure in outer space, what is it then that keeps water from boiling? There's only one thing left. What is it? Intermolecular forces. And guess what, guys? In outer space, intermolecular forces are not strong enough to keep the water together. Check this out. I hate doing this, but anything for science, right? Okay, so guys, what I've got here is a syringe with some water in it. Okay, now, when I pull, well, actually, let's do this. Why is this water not boiling right now? What's keeping it from boiling? Two things. What are they? Intermolecular forces and air pressure, right? The air pressure is pushing down through this nozzle. It's open. You can even see that. When I pull this down, air is there. You can see the air. The air is pushing down on the water. 88 pounds per that air. So there's a lot of pressure pushing down from the air and the intermolecular forces. And when I pull down, and you can see, anyway, okay, now, this is where this gets crazy. So what I'm going to do now is I'm going to do this again, but I'm going to stopper the tip of the syringe with my finger. Okay, and you'll see this is really hard to do. But imagine that my thumb is on top of the syringe. When my thumb is on top of the syringe, when I pull down, air will not be able to get in. And if air is not able to get in, what's going to be up here? Nothing. And if there's nothing up here, which we call a vacuum, if there's no air up here, what will be the air pressure? Essentially zero. We're basically sending this water into outer space. And when we do, there will no longer be air pressure pushing on the water. So what's the only thing keeping it together? Intermolecular forces, and you're going to find out that those are not strong enough to hold the water together, and the water will boil at room temperature. This hurts like crazy. I hate doing this. Because guys, look at what's going to happen. Right now, we've got air pressure pushing down and air pressure pushing up, right? Air is pushing in all directions. So when I pull down on this, the air pressure pushes down, no big deal. Basically, all I'm doing is moving the water. But here's the problem. When I stopper this with my finger, no longer will I have air pushing down. So when I pull down, air pressure is going to push up and keep me from doing this. And this is ridiculously hard. Remember, 88 pounds over the surface of a beaker. Guys, there's a lot of force pushing on this plunger. But watch what happens. Now, I've got to hold it like this, because if I don't, it's going to fly out of my hand. But guys, watch the water when I pull this down here. Again, I'm going to stopper this, and it's going to keep the air from coming in, and you're going to see the water boil. You ready? Oh, crap. Can you see the water boil? Can you see the bubbles? Can you see it boil? Does that mean the water's hot? Ow. Look at my thumb. That hurts. Okay, but guys, was the water hot? No, but was it boiling? You saw the bubbles. Guys, the water was boiling not because it was hot, but because the air pressure was gone. The intermolecular forces aren't strong enough to hold it together, and water boils at room temperature. I'll do it once more. Again, why? Do you understand why this is hard? Why is this hard to do? Air pressure. Because guys, I'm pulling down against air pressure, and that's how strong air pressure is. So here we go. So we're going to stopper this, pull it, good heavens, down. And you can see the water boil, not because it's hot, but because, again, there's no air pressure keeping it from boiling, and the intermolecular forces aren't strong. And you get the idea? Okay, I'm done now. Okay, so do you get the idea? So guys, this works in both directions. Decreasing elevation increases the pressure, boiling point goes up. But decreasing the pressure causes the boiling point to go down, so much so that we can actually get water to boil at room temperature. Was that worth doing, or should I just stop doing this because it's not worth the damage it does to my thumb? Sort of in the middle? All right. I may not do that fourth period. That is not fun. Okay. So guys, you good on this idea? Okay, so now guys, let's round out the conversation because now we're ready to talk about the lab. So this is half the picture. You now understand that one of the things we can do to make water boil at a higher temperature is increase the pressure by decreasing elevation. Now guys, let's talk about intermolecular forces. Don't miss this transition. So what could we do to make water boil at a higher temperature relative to intermolecular forces? Would we want to make the intermolecular forces stronger or weaker? Stronger. And guys, how on earth do we strengthen intermolecular forces? How are we going to do that? How can we make intermolecular forces stronger? Answer, add salt. Guys, in order to do this, in order to strengthen the intermolecular forces, what you do is you create a solution. That is actually what happened in lab on Monday. You added salt to water. The salt makes the intermolecular forces in the water stronger. That makes them harder to break, and the boiling point goes up. Did any of you write that in your conclusion answer? Did you really? Oh, you guys are smart. You got it. So guys, now what we need to do is transition and talk about solutions. And remember the triangle when we talked about hetero and homogeneous back in September? No, you don't. That's when you first learned about solutions. And guys, when you learned about solutions, you learned that they have a solute and a solvent. If you don't remember which is which, you may want to write this down. The solute is the thing being dissolved. In the case of the lab, that's the salt. The solvent is the thing doing the dissolving. In the case of the lab, that's the water. Okay, so guys, we're getting closer. We now understand what affects boiling water. And now we understand that creating a solution has an impact on intermolecular forces, so that changes boiling. So now what we've got to do is have another conversation about what happens when things dissolve. And then at that point, we can bring these things together and actually figure out the answer to the conclusion question. So guys, now we're going to have a dissolving conversation. Ready? And it goes like this. When we talk about dissolving, we talk about solubility. So let's define it. You should write this definition down. Guys, solubility is the measure of a substance's ability to dissolve in a solvent. And in this class, our solvent will always be water, so let's just call it water. So solubility simply tells us whether or not something dissolves in water. So salt is soluble in water. Sugar is soluble in water. Sand is not soluble in water. Oil is not soluble in water. So some things are soluble in water, other things are not soluble in water. So guys, the question then becomes, what determines when things do and don't dissolve in water? And guys, the answer is this, and here's how we're going to do this. I'm just going to give it to you. Write it down without expecting to understand it. Then I'll show you some animations and it'll make sense. You ready? So why do some things dissolve in water and other things don't? To talk about that, we got to talk about what are called aqueous solutions. So guys, what is the root word for aqueous? Aqua, which is the Latin word for water, which Spanish folks, Spanish speakers, got even closer to, because in Spanish, water is agua, which kind of, anyway, you get the idea. So guys, aqua is the Latin for aqua. It means water-based solution. So now we're getting closer. Because the question we're trying to figure out is, why do some things dissolve in water and other things don't? What we're really asking is, why do some things form aqueous solutions and other things don't? And guys, the answer is this. Here it is. When your 5-year-old comes up to you and tugs on your pant leg and says, "Daddy, why does salt dissolve in water?" The answer is this. Well, Junior, the reason that salt dissolves in water is because salt is polar, and as a result, the polar water molecules can grab a hold of it and pull it apart. But Daddy, why doesn't oil dissolve in water? Gosh, son, that's another great question. And the reason is because oil is not polar. Because it's not polar, the water can't grab a hold of it and it doesn't dissolve. Gosh, Daddy, you're so smart. See, this is actually a parenting class. You didn't know that. But guys, that's really the answer. In order for a solute to dissolve in water, water molecules, which you'd better understand are polar because they're not symmetrical, polar water molecules have got to be able to grab a hold of them. So guys, what things can polar water molecules grab a hold of? Other polar things. So guys, the bottom line is this. If it dissolves in water, it's polar. And if it doesn't dissolve in water, it's not polar. So I think you guys should go home tonight, grab a big old bucket of water, and then just wander around your house and randomly grab a hold of things, huck it in the water, and figure out if they're polar or not. How would you know? Well, if it dissolves, what do you now know about it? It's polar. And if it doesn't dissolve, it ain't polar. And guys, it's really that simple. Because water is polar, if something dissolves in it, that something is also polar. And if it doesn't dissolve in water, it ain't polar. That's why oil doesn't dissolve in water, because oil's not polar. There you have it. But guys, again, I don't expect you to fully understand that. Let me show you the videos and then it'll make sense. And then we'll be ready to answer the conclusion question. And we are about 15, 20 minutes away from being done, and you'll get your homework done today. Is this starting to fit together for you? Again, the thing we're talking about right now is why does stuff dissolve in water? What's up with the solution process? And we now understand that things that dissolve in water have to be polar because water can grab them and pull them apart. Can I go on? Do you have all this down? You're okay? Okay. So guys, let me show you. Showing you, I think you're going to find, is a lot more effective than telling you. So here you go. Ready for some animations? Kerpow. Here we go. So guys, what we've got here is we have got a flask of water. You'll notice that they gave us a diagram of water in the right-hand side. Guys, why did they show us what a water molecule looks like? Because what does that remind us about water? Is it symmetrical? No. Therefore, is it polar? You betcha. So guys, they're doing that to remind us that water is polar. So now that we remember that water is polar, check it out. They actually did a pretty good job with this. In goes, oh, did you see it? See this little thing coming down? You would think that that's a sugar cube. Oh, would you be wrong? It goes in the water. They zoom into it. They tell you it's salt. Then they show you that it is salt. Not too bad, right? I mean, they actually even got the colors correct. Not that green is really chlorine and not that sodium is silver, but those are the accepted colors, so they modeled it after this. So this is really kind of what a salt crystal looks like. So now, let's bring in the water molecules. Now, guys, remind yourself, what are the forces that are holding these water molecules together as a liquid? What do we call those? Intermolecular forces. And now look at what happens. These water molecules, remember, they are mosh pitting. They're running into all sorts of stuff. They start to run into the salt. And when they do, these water molecules, because they are polar, grab a hold of the ions in the salt crystal, and just like tugboats, they put their lines around those sodium and chlorine ions and drag them off into solution. But guys, what are the forces that are attracting the water molecules to the ions? Also intermolecular forces. So guys, the same intermolecular forces that hold the water molecules together are intermolecular forces that attract the water to the salt. But guess what? the attractions that the water have for the salt are stronger than the attractions than the waters have for each other. That's what allows it to dissolve. So these stronger intermolecular forces allow the waters to grab a hold of the salt ions, carrying them off into solution. There they go, and the salt dissolves. Do you get the idea? It's kind of hypnotic. And now it's all dissolved. Good? So what about sugar? Does sugar dissolve in water? Yeah, sugar dissolves in water. So now what do you know to be true about sugar because it dissolves in water? It's polar. But what does this look like? Okay. Oh, did you see that? You're thinking that's salt again, right? Oh no, that's sugar. So here goes the sugar. Sugar. I'll never do that again. That was kind of gross. And guys, what does sugar look like? Not this. It's not bad, but it's not great. I'm realizing I should provide a better model for what sugar looks like. But guys, sugar actually is different than salt. In salt, you've got sodiums and chlorines. In sugar, at each one of these locations, you have a molecule of C12H22O11. So you've got a sugar molecule here and a sugar molecule here and a sugar molecule here, and they still stack up like this, but each one is an individual sugar molecule. Well, again, here comes the water, and the water molecules mosh pit and slam into these sugar crystals. And sure enough, these water molecules are attracted to the sugar molecules, and they take this crystal and rip it apart. But guys, notice that when they do, the sugar molecules don't break apart. They come off intact. But in either case, the sugar and the water are attracted to each other, and the water molecules grab a hold of the sugar molecules and drag them off into solution, and they dissolve. Now guys, again, what are the forces that exist between the water and the sugar that allow them to get together? Intermolecular forces. And what do you know about these intermolecular forces compared to the intermolecular forces between the water molecules? They're stronger. Guys, if something dissolves in water, these attractions are stronger than the attractions between the waters. If they weren't, it wouldn't dissolve. So anytime something dissolves in water, these intermolecular forces are stronger. The water molecules continue to rip the sugar crystal apart until the entire thing is dissolved, and off it goes. You get the idea? You good? Okay. So guys, if you're good, let's answer the conclusion question. You ready? Here we go. We'll do some stop motion here. Okay. So guys, it goes like this. Let me bring these down a little more. And now we're ready to answer the question. Again, you don't have to change your conclusion answer, but you gotta understand this. So guys, here, actually, let's go all the way back here. So here's the deal. Here we've got a bucket of water, right? And in order for this thing of water to boil, what has to happen? Two things have got to happen to get this to boil. What are they? Have you not learned anything over the last 30 minutes? Guys, what has to happen to get water to boil? I heard somebody say intermolecular forces have got to break. What else? Overcome air pressure. So, in order to get this water to boil, we've got to break the intermolecular forces and overcome air pressure. So guys, the idea then is this. We're going to say that air pressure is constant because we're not going to change the elevation. But to get this water to boil, we have got to break the intermolecular forces, and the amount of energy that takes determines the boiling point. But now, guys, let's add the salt. So when we add the salt, in comes the salt. Let's go here. All right, there we go. Now what do we have to do in order to get the water to boil? Which forces have got to break? Now to get the salt water to boil, which forces have to break? It's no longer the attraction of water to water. What is it now the attraction between? Water and salt. Guys, it's now these attractions, right? It's no longer the water-water IMFs, it's the water-salt IMFs. And what do you know about these attractions compared to the water-water attractions? They're stronger. How do you know they're stronger? Because if they weren't stronger, the salt wouldn't dissolve. So guys, the fact that salt dissolves tells you that those attractions are stronger. Because those attractions are stronger, they're harder to break and the boiling point goes up. Do you get it? So guys, what about in sugar? What about if instead of salt we look at sugar? Well, if we go down here and if we look at sugar, come on. Oh, drawing dots. So guys, if we go down here and look at sugar, come over here, grab this. What about now? Will this be easier or harder to boil? Why harder? What forces have got to break now in order to get this to boil? Water-water forces? No, water-sugar forces. And what do we know about those water-sugar forces compared to water-water forces? They're stronger. How do we know they're stronger? Because if it wasn't, it wouldn't dissolve. And because these are stronger, they're harder to break and the boiling point goes up. So guys, the bottom line is this. We could go back to lab right now and we could redo Monday's lab and I could give you sugar instead of salt and the results would be exactly the same. And then we could come back on Friday and we could redo the lab and I could give you lawn fertilizer instead of sugar or salt. And the results would be exactly the same. It doesn't matter what you dissolve in the water. If it dissolves in the water, the boiling point will always go up. Do you get the idea? Questions? Okay, then let's see if you can summarize this. So guys, it goes like this. This is how we're going to wrap up the day. We're going to wrap up by summarizing. And guys, what we are now talking about, and you need this in your notes, what we are now talking about is something called colligative properties. So what are colligative properties? They are properties of solutions that are determined by the number and not the type of solute particles that you're adding to a solution. So what does it mean that type doesn't matter? Again, you could dissolve sugar, you could dissolve salt, you could dissolve fertilizer. It don't matter. If it dissolves, the boiling point's going to go up. So what does it mean that the number of particles matters? Well, guys, you saw that in lab. The more salt you added, the higher the boiling point went. So colligative properties are properties of solutions that are determined by how much stuff you add and not what type of stuff you add. If it dissolves, it will do this, and the more you dissolve, the more it will do this. So guys, here's the deal. There are dozens of colligative properties, properties of solutions that depend upon adding solutes. You only need to know two. The first one we just talked about. We call it the boiling point elevation colligative property. And you already understand it. Adding salt to water makes the boiling point go up. That's called boiling point elevation. Here's what you need to do right now. Explain why. In your own words, in your notes, explain why the boiling point goes up. Why does salt make the boiling point of water go up? And guys, you need to commit to this. And it is a cause and effect relationship. And it requires 3 steps, 3 logical steps. So guys, write down your best explanation, and then I'll share with you the way I think about it, And then we've got one more colligative property to think about and we're done. Is anyone feeling brave? Come on. Come on. You guys all, several of you raised your hand and said that you got the conclusion question right. You really going to make me do it first? All right. So guys, how does this stack together? Why is it that the boiling point goes up? Well, guys, I would suggest the progression of logic goes like this. First of all, if the solute dissolves, the intermolecular forces are stronger in the solution. How do we know that's true? Because if they weren't, it wouldn't dissolve. So the intermolecular forces between the solute and the solvent are stronger. So what? Well, guys, the next thought is stronger intermolecular forces are harder to break. So what? Well, if they're harder to break, the boiling point has got to increase in order to give them enough energy for them to break. So guys, that is actually the logical answer to the conclusion question. Dissolving a solvent or a solute in water makes the intermolecular forces stronger. Making the intermolecular forces stronger makes them harder to break. Stronger, harder to break intermolecular forces will have a higher boiling point because you got to add more energy to get them to fall apart. You good? Do you love it? All right. So guys, we got one more to go and we're done. This is the one that's interesting, and I'm going to see if you can think your way through this. So guys, when you add salt to water, you now understand that the boiling point goes up. But that's not the only thing that changes. Guys, surprisingly, the freezing point also changes. But it doesn't go up, it goes down. Guys, the freezing point depresses. We call this the freezing point depression colligative property. This is why we put salt on our roads in the winter. When we add salt to the ice on our roads, it causes the freezing point to go down. And if we can get the freezing point to go down below the temperature that it is outside, the ice will melt and then it's safe to drive on. So guys, this is why we put salt on our roads. Makes the freezing point go down. If you can drive it down below the outside temperature, the ice melts and you're good to go. The question is this: why would adding salt to water make the freezing point go down? Thoughts? Why would adding salt to water make the freezing point drop? Let's let people think about it for a second. Guys, why would that happen? Why would adding salt to water make the freezing point decrease? Go ahead. Say that again. But that would make it, she said, as with stronger IMFs, doesn't that make it closer to freezing? And if that's the case, it would freeze at a higher temperature, right? Because it would be easier to freeze. It would be the opposite. Guys, any thoughts? Why would adding salt to water make the freezing point go down? It does have to do with stronger IMFs, yeah.
You have to remove more energy to separate the salt molecules from the water molecules.
That's it. Guys, check it out. You ready? Here's the idea. What is this? What does this represent? Ice. This is what ice looks like. It is amazingly organized and structured. The intermolecular forces hold the molecules together in fixed positions. They sit there and vibrate. Everything that you know to be true about a solid. But guys, you'll notice that there's no salt contained in the ice. Did you know that? That when salt water freezes, the salt gets left behind? If you don't believe me, try it. Make a little cup of salt water, throw it in the freezer, and the top layer where you'll actually get the ice, that's pure water. There's no salt in the ice. Chip it out and taste it. It won't taste salty. There's no salt in the ice. Because guys, this is what happens when salt water freezes. Can you hold that for me? So imagine that this is our ice crystal and this is our salt water. So this water molecule is attracted to the salt. So what does this water molecule have to do in order to freeze? Well, this water molecule's got to come over here and find a spot where it can connect to the crystal. But the problem is this water molecule is way attracted to this salt. And if this water molecule is attracted to this, it's going to be harder to get it to go over there and freeze. And because it's harder to get it to go over there and freeze, you got to cool it down lower to get this water molecule to go, I'm done with you, I'm going over here, and I'm going to go be ice. You get the idea? So because the water is attracted to the salt, it's harder to get it to be attracted to the ice crystal, and as a result, you've got to cool it down lower to get it to freeze. That's why it freezes at a lower temperature. So guys, let's summarize that and see if you get the idea. So it goes like this. The progression of thinking for freezing point depression goes like this. If the solute dissolves, we know that the intermolecular forces are stronger. Same thing as here, right? But why does that impact freezing? Well, guys, the answer is this. These stronger attractions, as Matt said, make it harder for the water to get together and form a solid, to form structure. As a result, you've got to cool it down to a lower temperature to get it to freeze. That's why the freezing point goes down. So there you have it, guys. Please do not go back and rewrite the conclusion answers on your lab. I promise you I won't grade them. Really, all that you need to do now is graph your data. Be careful that you do that well. We'll turn those in the day of the test on Friday. Guys, in front of you, you have your homework. Oh man, we got half an hour. So you got a really good shot at getting your homework done today. So if you want to dig into that, the answers are on the wall. Notice that all of these questions are qualitative. They're descriptive. They'll help you think through the things that you learned today. And then guys, please go back and look in December as you're studying for this test. You're going to be glad you did. So guys, we do have half an hour left. If you know that you have late homework or late lab work from this unit, well, any late lab work, late homework from this unit that you need to turn in, now would be an okay time to do that. If you need help on the homework, let me know. And guys, we'll do pride reports as we get closer to the end of the day. So go get them. Go get them, go get them.